had spoken about saddle points in the last lecture, where you saw how nicely, without much information about the problem, only knowing that the problem is convex and an additional condition like Slater condition holding true, you can get a neat optimality condition expressed through the Lagrangian function. Now, let us look at the Lagrangian function slightly more carefully and the saddle point condition. So, the saddle point condition says that if you give me a minima, then I can find a lambda bar if x bar is the minimum of the convex problem such that this occurs. For all x in some capital X and lambda element of R m plus. Now, if you look at it, there are two aspects of this, that if I fix lambda bar, then L x bar lambda bar is the minimum value over x of L x lambda bar. Now, fix x bar, then L x bar lambda bar is a supremum value. Okay, we take it as a maximum value because x bar lambda bar, if I put lambda equal to lambda bar, they are equal. So, maximum of lambda element of R m plus L x bar lambda. So, here x bar is fixed, here lambda bar is fixed. So, we were actually solving a convex minimization problem, and now here the Lagrangian function by which we converted a constant problem into an unconstant one, somehow unconstant because we have not been able to handle this abstract constant directly. If x is equal to R n, then okay, this problem is truly an unconstant problem. So, if we were actually doing minimization problem, how does a maximization problem always arise? How did a maximization problem come to the scene? So, the question is, behind every minimization problem is there a maximization problem going on? That is the question. Now, what is the answer to this? Let us look at search for answer in a much more interesting scenario, in a more real life realistic scenario of games. So, now we are going to discuss what is called a bit, not really very deeply, but we are going to discuss what is called 2-person zero sum game. Any interaction between two human beings, for example, is a game. It could be interaction between two human beings, it could be interaction between two armies fighting each other, it could be interaction between two football teams playing football or two cricket teams playing cricket. So, any interaction between a conglomerate or group of people or individually between few people, such an interaction is called a game, and of course, there are rules laid out. So, in a 2-person game, the stuff of the games are two players, which I call as player 1 and player 2, and everybody has certain strategy to play the game. Chess players of course have an extensive strategy to play. So, they know the opponent, okay, possibly this is the way the opponent is going to fight me. So, this would be my strategy. So, mathematically speaking, let there be a convex compact set in R n which is the strategy of player 1. Just take it Rn for simplicity. So, this is strategy set of player 1. So, all his moves in the game. So, what happens in a game is player 1 makes the move, then player 2 makes another move. So, all his moves are recorded, he has stored in this set called X. Strategy set of player 1. Now, let Y be the strategy set of player 2 and let us assume this to be convex compact. Rm. So, these could be mixed strategies, you know. So, those who know some game theory, so it could be a simplex actually, because it holds the probabilities of the moves. So, here we are doing it in slightly abstract fashion. The strategy set of player 2. Now, of course, it is a win and loss situation, means somebody is winning, somebody is losing the game. So, how do we write down the game? What more we need? It is like playing, I mean, it is like gambling, you know, that every game, you know, a lot of this mathematics has come out of gambling. So, here when x makes a move and y makes a move, and depending on the two moves, the player 1 has to play some money to the player 2. If that money is positive, then he actually has to pay, if not he returns, I mean he gets a similar amount back. So, given a strategy x which is in x and a strategy y of player 2 which is in y, this is the payoff of 1 to 2. So, basically I can write this as player 1 player 2. So, it has a strategy set x, it has strategy set y. If he pushes in x and if he pushes in y, then kxy is the amount of money in paid by player 1 to player 2. Now, if kxy is greater than equal to 0, then 1 is paying to 2. If kxy greater than equal to is strictly less than 0, 0 is ambiguous, not ambiguous, but you can just decide, then basically no one pays anything, then 2 pays 1. Now, what happens is that if kxy, if 2 receives kxy, then 1 loses the player 1, these 2 and 1 are marking the players, and 1 loses kxy, and so he gets minus kxy. So, the total sum is 0, total payoff is 0, and that is exactly 0 sum game. So, it is basically like this. For example, I can devise a game standing here. So, I play a game with you, a game is that I will tell a country, you have to tell me the capital city. So, you know strategies, you have a strategy set of all capital cities, and another set is the country which I have. Now, I make a move country and you give a capital city. Now, if the country and capital city matches, then I pay you 1 rupee, and if the capital city and country does not match, you pay me back 1 rupee. This is an example of a 2% zero sum game, and Okay. Now, what can we look into from here? What can we conclude from here? So, how do the player knows that what is actually their end result? That is, how do I know that there would be a strategy which would possibly be best for both, that there would be a strategy which is optimal for both. So, if I move off from that strategy, both are not in a good position, or one is in good position, other is not. So, what is a strategy which tells me that okay, this strategy is the best strategy to take when. So, let us see what happens. What does player 1 do? Player 1, let us see, let us look at an argument player 1 will take. See, he has to pay money. So, he knows that suppose this guy player 2 has given input y, he has played y. Now, he knows that given this y, I have all elements x in x, capital X at my disposal. So, I can plug in any x I want. So, corresponding to every x, he has to pay k x y. Now, he would like to know what so if given me, once the y is given to me, I know what player 2 has given. He wants to know what is the maximum loss he can make. So, this is the maximum amount of money he has to give, the maximum value of k x y. This is the maximum loss, because of this, I assume the continuity and all nice properties. So, there will be an x naught in x for which this minimum and maximum would actually occur. So, if he chooses by mistake, that is the strategy, that would be his maximum loss. So, but nobody wants, sorry, I am making a little bit of mistake. I am telling from the point of view of player 2. I should tell from the point of view of player 1, just a bit. It happens, you get carried away in your thoughts. Okay, let us go back again. So, as a player 1, I am pushing in a strategy x, right, and you now know that y can give in any strategy. I have given x, but I do not know what strategy y will play. So, I was just telling the reverse thing, I should have written it here. So, I do not know what is the strategy player y will play. He can play any y at his disposal. So, he keeps on giving a y. So, how do I know what would be my loss, how much money I have to pay? So, the maximum money I have to pay, my maximum loss is max of. So, there is a strategy y, small y, if that is played by player 2 corresponding to my given x, player 1's x, then that would be, this would give the maximum loss. Means because the function is nice, because of the compactness of capital Y, there exists a y naught for which k x y naught is the maximum value of this. Suppose for my this particular x, the guy puts y naught, then I lose a large amount of money. So, I want to know what is the maximum money I am actually losing. If the player 2 is putting in the, if I put the strategy x and player 2 has the right to put any strategy he wants, what is the maximum amount of money I am losing? This is the maximum amount of money I can lose if I put the strategy x. So, player 1 knows that if he puts in a strategy x, this is the maximum amount of money he will lose. Now, what is his aim? He wants to play such a strategy x which will minimize this loss, minimize the maximum loss. So, this being minimized over y, so it is a function of x, because as you change the x, the value of the maximum value will change. So, what player 1 intends to do is to minimize over this, is to minimize this function phi. So, basically player 1's problem is what is called a min max problem, minima over x, maxima over y of k x y. So, player 1 is actually running a min problem, This is his final problem. Let us see what player 2 does. If player 2 can put in whatever strategy he likes. Suppose he chooses a strategy y. Corresponding to this input y of player 2, he knows that player 1 has at his disposal any strategy from x. Now, once he has this thing in his disposal, the interesting thing that comes out is the following, that okay, you have x in your, this guy player 1 has any strategy he likes, but given his strategies, he might choose such a strategy x for my given y, he might choose an x naught, so that for all possible k x y values for this fixed y, that would give me a minimum, that will give me the minimum value that I can get by playing this strategy. So, he wants to know what is the minimum amount he can make, that is his goal. He does not bother about what is the maximum amount he is making, he is not greedy at the beginning. He says, I just want to know that if I play y, what is the least amount of money I am going to get, this is the least amount of money he is going to get, which because you are minimizing over y is a function of minimizing over x is a function of y. So, you see now this is the minimum amount I will get, but my aim would be to play such a strategy y, so that I can have as much as I can from that minimum amount. So, I will have what I will do is max of, and you see voila. So, this is absolutely fabulous. So, what I have is a max mean problem. So, the player 2 is actually playing a maximization game. Basically, his problem is to maximize a function, player 1's game is to minimize a function. So, this is exactly what player 1 is doing, and this is exactly what player 2 is doing. So, you see even when you are talking about games, there are two problems that is going on, that if there is a minimization problem, there is a maximization problem. Of course, one of the major problems of game theory is to know when is mean max over max over y, mean over x, and max over y and mean over x. When is this equal? That is the question. That is a central question of game theory. If there is a pair x bar y bar for which these two values are equal, then such a pair x bar y bar is called the value of the game, that is the equilibrium. Means if you deviate from this, one of you are in the downside. So, we will not go into discussion of game theory at this moment. So, there is another reverse question I want to ask. Can the usual optimization problem, say a convex optimization problem of minimizing a function, a convex function over some convex inequalities, say, can be posed as a min max problem? Okay, that is the question. So, then correspondingly we can think that there is some max min problem somewhere associated with it. So, this is what I will call the primal problem, this is what will be called the dual problem. So, my question is this: given Cp, that is minimize fx, take this simple problem, do not bother much about anything else. Can this problem be posed as a min max problem? So, this problem is called a min max problem. Can it be posed as a min max problem in the sense that can you define first some k x y, that is to define a min max problem there must be function of two variables, two vectors x and y, because you are maximizing over y and minimizing over x. So, if I give you a min max, I give you this particular problem, if I ask you can you pose it as a min max problem, your first question would be how do I pose as a min max problem, I just have one variable x here and where is my k x y. Then you think a bit, no, there is something. The something is okay, let me write it like this, L x y as f x plus y 1. So, I can from this problem I am creating a function of two variables, okay, go on. So, where I call this is in R n and this I take in R m plus, your strategy set, just like your strategy says. This is your k x y, you have replaced k x y with what is known as, this is familiar to us, this is the Lagrangian. Now, you say okay, associated with a convex problem C p is its Lagrangian function. So, can the Lagrangian function be used? That is an interesting question that comes. Anyway, this is the way naturally people would argue. Now, if I have been able to associate a function of two vectors x and y associated with the problem C p, can this be used to pose C p as a min max problem? Answer surprisingly is yes, but here we will not write min max, but instead we will write inf sup, because we do not have compactness here. So, if the engineers do not understand what I am telling, the inf sup and all these things, do not bother, you can just replace whatever I am writing as inf sup in as min max. So, it will be loose in some sense, but it will give you some understanding. So, okay, let us look at the supremum of L x y when y is greater than equal to 0, in the sense that y is in a R m plus. Okay. If you do not like this symbol which reminds you of real numbers, so I will just go and write it like this. This is exactly this first step, the first step here in k x y, that k x y max of k x y, this is exactly the step, and this step is what we are doing at this moment. Now, what does this give me? This gives me something interesting. Now, if I pose that every y 1, y 2, y m are greater than equal to 0 and I take x to be feasible, that is x such that if this is what I have, that I have taken x which is feasible, then y 1 into g 1 x, y 2 into g 2 x, y m into g m x, all these are less than equal to 0. So, when this happens, let me do the calculation on the side. If x is feasible, L x y is less than equal to f x for all y. Now, if I had chosen all the y 1, y 2, y m's as zeros, then L x y would be exactly equal to f x. So, f x is a value taken up here. So, the supremum, or in fact the maximum actually, of L x y, y element of R m plus is equal to f x. If you have not understood this argument, note that if I choose y is equal to 0 here, then L x 0 is exactly equal to f x. So, in that sense f x is, this is true for all y. So, L x 0 is less than equal to f x. So, f x is less than equal to f x, right. So, which means since f x value is one of these values, so this is f, this supremum is attained. Actually, now I can also write. So, when x is feasible, this is what it is happening. So, this is what I write down. And now, suppose x is not feasible. If x is not feasible, so there can be two cases only, x is feasible, x is not feasible. So, if x is not feasible, then there must be some I, that among the 1, 2, 3, 4 m constraints, that g I x would be strictly greater than 0. Assume that g 1 x for this particular, take an x for which g 1 x is strictly bigger than 0. So, what I will do is I will put the y's equal to 0 for all the rest and keep on increasing the value of y 1, and I can keep on increasing and it will blow up, which means what I have is the following. This is exactly your effective function, effective objective function, the that you can pose optimization problems as extended valued optimization unconstant problems with extended objective function, extended valued objective function, that is function that takes both plus and that can take plus infinity value also. So, you get back this. So, what is my problem actually at the end? My problem Cp is equivalent to the infimum of over Rn supremum So, this is my primal problem. The usual problem Cp is now looking like this, is I have posed it as a min max problem, inf sup problem. What this is exactly what question I have asked you. Now, you might now question, okay, going back to the min max problem and max min problem, remembering what player 2 does, is there any problem which I can set like this, like I can change the position sup of y if I write a problem like this, because I am just imitating what I have done for player 2 in this case. You see what I have done for player 2 is this problem, max then mean of the payoff. So, suppose I write this problem, is there any relation? That is the important question, is there any relation? Now, if I break up this problem a bit, then I can write theta of y, which is your psi of y here. So, theta of y I can write as infimum Now, the dual problem is supremum, this problem which I call the dual problem. So, given the primal optimization problem, by following the things that we have just learned from 2% zero sum games, I can mark this problem as DP or the dual problem. What is the relationship between these two problems? Okay, just like the game theory guys did, I can ask this question again, that is if inf of so this is the minimum value. So, if I want to find the minimum value of f x or infimal value of f x, does not matter, x element of the feasible set C is this. Now, inf sup, you look at inf sup here, just like the game theorist, can I ask this question, is inf sup Lxy okay, this is over y, this is y element of R m plus and this is x element of R n. Is this then equal to, like the game theorist I am asking the question, your problem is convex. So, you might have some interior feeling that convexity had been good for so long, maybe it will not behave badly right now. Mind, as you know, keeps on wandering. So, wandering as well as wondering. So, you can forgive me for this little hang ups. The question is this true if you have a convex problem? That is that question. If this is true, then we said strong duality holds. Now, question is this always true? That is now an interesting question. You might take it as, I will not give you this question as homework, it is a thing that you need to ponder upon, because this is one of the central facts and a beautiful fact of optimization theory. That is why that is what makes it an elegant subject. Now, let us see what we can do out of this. So, this is sometimes called value of Cp, minimum value of f over those this value, and this is called the value of dp, dual problem. So, what question, the major question lies is, this is quite a tough question, you just can't figure out immediately that this will be equal or not. But most little bit of examples that you can try out at home. Take a simple convex problem, I give you a convex problem. So, is the above fact, which I can write as star now, true? Just check it out, you will find it is actually. For most convex nice problems it is. Now, instead of asking such very stringent question, equality is a stringent things. For many people equality might be something very beautiful, precise, because it is telling that two functional value, objective values of two different problem, one is a maximum, one is a minima, is actually equal, is a very big statement. But is there something slightly loose I can say? For example, any functional value for any feasible element in C, for any x in C, f of x is definitely bigger than equal to the value of dp. So, if you take any feasible x, if suppose this is true, then f of x, for any x, f of x is always bigger than equal to Cp, bigger than equal to dp. So, is there something slightly loose, means let us see, I can get something not so stronger, but something loose which can just work through. Now, let me look at f of x plus so this is my Lagrangian function, just to recollect from here, and now let me figure out some relationship between them. Now, suppose x is feasible, and y of course is in R n plus, then this whole portion is negative and less than equal to 0, non positive to be precise. then this portion is obviously less than f x, because they have added a negative quantity to something. So, that value of that quantity decreases. So, f x is bigger than equal to L x y for any x in C, which is the feasible set, and y element of R m plus. Now, let me fix up the y in R m plus. Let me fix up the x that I have taken in C, and I keep on varying the y. So, whatever y I take, this is the story for this particular x. So, for a fixed x, f of x then you think, oh, what can I do if I fix x? I cannot move. Okay, let us not fix y. Fix, nothing can be done. Now you see, I cannot, if I fix the x, then I have to operate something on y, but on y I have to I am always maximizing on y. So, I just cannot take this step first. So, let me just change it. So, for a fixed y, this is true for all x in C. So, I am C. This is how one would argue. Now, once I get this, this would immediately mean the following, that now what I can do is my y is fixed, but my x is varying. I can write inf of x over C of f x is bigger than inf of x over C L x y. And now, once y is fixed, the infimum over a smaller set would always be bigger than infimum over a larger set. Now, this is nothing but the value, that is what I was saying, value of the problem Cp, which is bigger than infimum Now, I have done it for a fixed y, but this is true for every y. If I take one y, this argument holds, take another y, the same thing will hold. So, this is true for all y, which tells me that value of Cp is always bigger than theta y for all y. This would imply that value of Cp, now value of Cp is a fixed number. So, I can operate supremum of y on both sides, but the supremum will have no effect on this side because it is independent of y. So, this would finally boil down to the following fact, this is value of dp. This will say that value of Cp is bigger than equal to value of dp, and this is something which we got in a very straightforward way, and this is called weak duality. Now, how to, under what condition will equality hold? The answer is surprisingly beautiful. If Slater condition holds, then equality holds. If Slater condition fails, equality may fail. But then you ask a question, is there any subclass of convex optimization problems where strong duality will always hold? And that class of optimization problems is called a linear programming problem. If my objective and constraints are linear, then strong duality will always hold. So, tomorrow in the next class, I would prove the strong duality theorem under Slater condition for the convex case. We would then construct for certain very special class of convex problems what is the Lagrangian dual, say for a linear problem for a semi-definite programming problem, and then knowing that linear programming is very special because without any condition the strong duality holds. We will get into the pleasures of linear programming. See, what does this result tells me? It tells me that if my value of dp is finite, that is if dp is feasible, which it is always, because y element of Rm plus, then if it is feasible and this value is finite, then value of Cp, and if Cp is feasible, I know what is the lower bound to Cp. I know that this problem has a solution in the sense that it will have an infimum, but I do not know whether there will be an x where that infimum would be achieved. So, with these little facts we stop our lecture today here, and tomorrow we will get into the beautiful world of strong duality, compute duals for certain class of functions, certain class of problems, important convex problems, conic problems, semi-definite problems, and then we will start taking a journey into looking into those special problems. And the first journey we will take is into linear programming, and not just linear programming, as I tell you, we will take a journey into the pleasures of linear programming. Thank you very much.